So now that we know the difference between alleles and genes, and allele frequencies and genotype frequencies, we're going to work through an example problem. And you can see that I've already put up on the board our equation to find allele frequencies, p plus q equals 1, and our equation to find genotype frequencies, p squared plus 2pq plus q squared equals 1. And this is under Hardy-Weinberg. Memorize these. Know them, love them, learn them. Know which one goes to which one. Just do it. It's the only thing I'm ever going to ask you to just strictly memorize. Just do it. It'll help you so much. All right. Always write those first. That way you know what to refer back to. So we're going to do a problem in which we know, and those of you who came to the homework help session, we did this problem in the homework help session, so you can either watch it for fun or skip over it. But we're going to do a problem where we know the number of individuals in the population for each specific genotype. We're going to find their allele frequencies. We're going to find what we expect their genotype frequencies to be if the population was a Hardy-Weinberg equilibrium. And then we're going to compare our actual genotype frequencies versus our expected genotype frequencies to see if the population's at Hardy-Weinberg equilibrium. If they're the same, then it is. Those genotype frequencies don't change from generation to generation. No evolution is occurring. If they're different, that means something's going on, and that's the fun part. So we'll start with a really basic problem, and I hope you guys can all see this. So we know our individuals in the population at each genotype frequency. We know that we have 250 individuals that are big A, so they are homozygous dominant. We have 251 individuals that are big A, little a, so those are our heterozygotes. And then we have 334 individuals that are little a, those are our homozygous recessives. So the first thing we want to do is know what? We want to know how many individuals there are in the population total. So we can add these up. And we get 835. So we have 835 total individuals in the population. So the first thing we want to do is find our actual genotype frequencies of the population. And that's super easy. You just take the number of individuals with each genotype and divide by the total number of individuals in the population. So you would do 250 divided by 835, 251 divided by 835, and 334 divided by 835. And we get these are our actual genotype frequencies. And if you did it right, they should add up to 1. So 0.301, 0.299, and 0.4. That looks like it adds up to 1. So we know we did it right. So now what we need to do is we need to calculate our allele frequencies. And we know, what do we know? We know allele frequencies, p plus q equals 1. Well, that's great, but we can't use that yet. What's p and what's q? So we need to find one of our alleles the hard way at least. I prefer finding both the hard way because that way you know you did the math right. And if they both add up to 1, then you know you've done a good job. If not, you may have done something wrong and you won't know because you're just subtracting from 1. I use the 1 as like a check yourself. Alright, so there's 2 ways to find your allele frequencies using given genotype frequencies. The first way is the way that Dr. Bernal went over in class, and you can count the number of alleles. So we know that we want to find what? The alleles. So we want to find the big A and the little a. I always try to write down what I'm looking for first with math because you can get lost real quickly. How many big A's are in this population? Or what proportion or percentage of the population has a big A? So we know that in our homozygous dominance, we've got 2 copies of the big A. We have 251 of these guys. So we do 2 times 251. Does everybody see how I do that? You do 251 and then 1A, 2A. So 2 times 251. Then you want to add, because you've got a big A in that heterozygote as well. And 250 of those. You only do one because they've only got one copy. Then you need to divide. What do you divide by? Well, the total population, but not just the total population. The total population is 835, right? But every individual in the population has 2 alleles. So you need to multiply it by 2. 0.4503. That's your big A. That is equal to your P. Now from here, you can do one of 2 things. You can calculate little a long way, or you can rearrange this equation to find Q, now that you know P and 1. I like to do it the hard way. So little a we'll find doing the other way, find allele frequencies. Can't get them confused. Pick one or the other. Can't get them confused. This way, you do number of individuals. So we do little a. How many people are little a? 334. We're doing this a different way than we did the first one, just to show you the 2 different ways to do it. So 334 people that are little a. And then we also have that little a hiding up here in our heterozygote, which is 250. But only half. See that? Only half of them, technically. They all have a little a, but half. So you do 1/2 times 250. And since we're looking at individuals, we just need to take this over the total number in the population, not the total number of alleles in the population. Which is why I like this way, because then you don't have to multiply a big number like 835 by 2. You just take it over 835. So you just do the total number of individuals that are the homozygous plus half the number of individuals that are the heterozygotes divided by the total number of individuals. And that gives us 0.5497. It's cute. And I like doing it longhand because then you can add these 2 up, and if you get 1, you did it right. If you didn't get 1, you did something wrong. Go back and check math. So it looks like these are going to add to 1. That is how you calculate allele frequency. I'm writing really big so that you guys can see this, but basically what I did was I just erased all that work, and then I rewrote our actual genotype frequencies and the allele frequencies that we just found up here. So I saved those because we need those. So what we're going to do now is we're going to calculate our expected genotype frequencies if the population was at Hardy-Weinberg equilibrium. And we use this equation now with the information that we just found using the allele frequencies. So we know p squared plus 2pq plus q squared equals 1, right? And so each of these terms is a different genotype frequency in the population. So p squared represents big A, 2pq represents our heterozygote, big A, little a, and then q squared represents little a, little a. Some people sometimes ask, why does P represent big A and Q represent little a? It doesn't really matter. It's just convention. That's how we do it. You can switch it. You can make P represent little a and Q represent big A, but it might get confusing later on, so I would recommend just sticking with convention unless you feel creatively inclined and you need to switch it. And that's okay as long as you carry it the same and define it in your problems. Alright, so what we're going to do here is we're going to solve for these individually. So we're not going to try to solve this equation as a whole. We're going to solve for these individually. So we know our big A is equal to p squared. We know our p value from up here. and we just square them. And we get 028. And we do the same thing for the other pieces. So our big A little a is equal to 2pq. That's the term that represents our heterozygote. And we do 2 times 0.503 times 0.5497. Heterozygote. And then what's left? Homozygote recessive. Q squared. And that's our homozygote recessive. Okay, so now what? So we have our expected genotype frequencies under Hardy if the population was at Hardy-Weinberg equilibrium. We have our actual genotype frequencies. We know from the numbers that we were given in the problem. How do we know if the population is evolving or not? How do we know if the population is in Hardy-Weinberg equilibrium? What we need to do is we need to compare our actual versus our expected. And to do this, I usually set up a chart. So we have our 3 genotypes, our actual, which we're going to fill in our actual genotype frequencies, and our expected at Hardy-Weinberg genotype frequencies that we just found in the previous step. So go ahead and plug in our actuals. This is really easy. And then our expecteds that we just calculated. And then we can compare them. Are they the same? Definitely not. So we know, because our actual genotype frequencies are not the same as our expected genotype frequencies under Hardy-Weinberg for the next generation, that this population is evolving. Something is going on here that violates one of those 5 assumptions of Hardy-Weinberg theory. What's going on? Well, we can take a closer look at these numbers and figure out where the differences are. So our expected homozygote dominance is a lot lower than our actual homozygote dominance. Our expected homozygotes recessive is lower than our expected homozygotes, than our actual homozygotes recessive. Actual heterozygotes are a lot less than our expected heterozygotes. So this is probably some form of disruptive selection. So what we see is a graph that looks like this, where you have your homozygotes on either end and your heterozygote in the middle. And you see something that is affecting the population so that the heterozygote number is actually a lot lower than it should be, and that your homozygotes are a lot higher. All right. So that's the end of that problem.